once we're able to solve for this omega and z, we're able to impute the missing data by computing the projection between the omega matrix and z vector. So that's it. Anyway, before we go, just to let you know that because of the fact that if we cannot observe every pair of ij in X, this problem is hard to solve. And I think part of the reason is because that means, it's like if you want to solve for omega and z, you have to actually solve this optimization by, trying to find the omega matrix and z that you sample from some random number and make sure that it fits this optimization problem, which could be very difficult because you're no longer able to use the whatever you learned previously about the eigenvalue, eigenvector decomposition. Eigenvalue and eigenvector decomposition would only work if you have the complete X, like in this previous formulation. If X is incomplete, you cannot decompose omega and z using the eigenvalue decomposition. But because now it's incomplete in this case, we have to use an iterative method for matrix completion. So yes, that will be our last algorithm for today. So in this algorithm, we will first initialize the X matrix. You can think of this X tilde matrix as this X matrix that contains some missing value. But we will start off because our X tilde contains some missing value, then we cannot really use the eigenvector, eigenvalue decomposition. But the thing is, in this iterative algorithm, they will actually first try to interpolate some value in this missing value with the average value along the feature dimension. After they interpolate this value, they will start to decompose the eigenvector and eigenvalue from this X. Actually, you have to do it from X transpose X. Once you have this eigenvector, you will put this eigenvector, which is like the phi, like the row of phi matrix, right? You put them together, the eigenvector matrix, the eigenvectors into a matrix. After that, in fact, once you have this eigenvector matrix, you can compute omega by using pseudo-inverse. And once you have omega, you are ready to interpolate the value back. And if you ask me, okay, you have omega, but what about z? Z is the projection from X. Okay, Z is the projection of X and phi matrix, right? So you can compute Zj anyway. So all you need is a phi matrix. Okay, you need phi matrix to compute inversion so that you get the omega matrix, and you need phi matrix to compute Zj. But you can only get that phi matrix if X is complete. So that's why this algorithm first starts off with interpolating some value of X matrix as the average value along feature dimension. So that means, in this case, like if, let's say this one is missing, what they did is that they compute the average along the column. right? And interpolate as the value of the missing one. And as you can see here, if you look at the algorithm, they first initialize that X matrix like that. After that, they compute for omega and SAT using the eigenvector and pseudo-inverse. Then you get this omega and SAT. After you get omega and SAT, you can compute the missing value using the matrix vector projection. Once you have this projection, you can then compute the original objective loss, which is the loss function of this optimization problem. And then you can verify if whether or not you get this loss reduced from previous iteration or in your starting point. After that, you would repeat the steps by once you already have this X tilde, that means you can now replace the missing value in X matrix with some X tilde, right? And then you can repeat again. You can compute omega and Z again. And once you have a new set of Z and omega, you can now recompute this missing value again. So you want to iterate until your loss is no longer improved. And that's it. Your result, the output from this will be the X tilde, the missing value. So that's the algorithm. So yes, actually you can apply this for many systems, and this is just one of the use case where we are considering the Netflix movie rating, where here's the customers are actually, in this case, what I find is kind of weird is like they actually use customers as the indices for the feature dimension and use the number of movies as the dimension for your samples. I mean training samples, J samples, and this is I. It's kind of weird for me because I normally thought that you have unlimited number of customers, that should be J, the other one should be I. But anyway, you can look around so for how they actually relate the information, because what is important here is like if you have like omega matrix and SAT vector that are representing this customer's rating, what would the reduced dimension be referring to? I mean, what is the latent SAT should refer to? In here, they actually use SAT to refer to maybe group of user that like certain movie or the genre of that movie. So it depends on what will be your interpretation. In this case, because they use J to represent the movie, like the J indices for your movie, then set J, which is like the reduced vector sample, is representing the score for each genre. So genre is related to the movies, and the clicks is actually related to user, like group of user that like certain movies. So that's it. It's like a use case. So please don't worry. But anyway, feel free to go back and play with the code that I referred to, and you can look at this link for example of what the eigenvector and eigenvalue are.